All right, welcome to Astronomy 1304, Solar System. We're going to talk about everything to do with the solar system. Well, where does the word solar system come from? Well, it comes from sol, where sol means sun. Okay, or Latin for sun is sol. And the question is, then, everything related to the solar system, or everything that is under the direct influence of the sun. Which means that not only gravitationally, but can also be within the magnetic field of the sun, is also considered part of the solar system, or everything that formed at the same time as part of the solar system. And we'll get to more of that later, what that really means. But the first lecture I'm going to talk about today is we're going to talk about stuff that should be reviewed for you, should have been reviewed from like 3rd grade. So let's just evaluate what's in the solar system. As we started first, we have the sun. And the sun is 99% of all the matter in the whole solar system is in the sun. So it is very significant. All the rest of the stuff is trivial compared to the sun. Wherever the sun goes, it just drags us along with it. Okay, and then we get to the closest planet. The closest planet to the sun is Mercury. And as we go out, the planets take longer and longer to go around the sun. Mercury goes around the fastest. It goes around in about 88 days. So it goes around about 4 times per 1 Earth year. Venus, on the other hand, is about 225 days. So it's about 3/4 of a year, or about 2/3 of an Earth year. Notice that Venus and Earth here, remember this is drawn not to scale at all. And later on we're going to talk about the scale of the solar system. These are not to scale, but Venus and Earth are about the same size. Mercury is much smaller. Mercury is about the size of our moon, just a little bit bigger than our moon. So it's significantly smaller. All right, after we get past Earth, we get to Mars. Okay. And we tend to bunch our planets into 2 types. The ones that are in here, we call terrestrial. Terrestrial planet. Terrestrial means Earth-like. So all these planets are Earth-like, meaning they're solid, rocky, small. They're all fairly close to the sun. So these are terrestrial planets. Once we get beyond Mars, then we go to Jupiter, the largest planet, Saturn, which has this spectacular ring system, Uranus, and Neptune. And these planets, we all categorize these as what we call Jovian planets. And remember, Jove is the Greek word for Jupiter. So Jovian means Jupiter-like. So these are all Jupiter-like. These also sometimes called the gas giants. These are mostly gas. Probably a solid core down at the center, but most everything we see is just gas, where these are all rocky, solid objects. Okay. There's other parts of the solar system too. In here between Mars and Jupiter is the asteroid belt. And then out beyond Neptune, there's a whole bunch of objects, what we call TNOs, for trans-Neptunian objects. They also have other names for them too. And we'll talk about those later. That's where Pluto is. So Pluto is not one of the planets. So we only have 8 planets that we have to, that are the main objects in the solar system. But right away, I want you to look at something. This tells us a lot about our solar system. When you see pictures of our solar system, they're always drawn like this. But there's a reason for this. Is all the planets in the solar system go around the sun, but they all go around the sun in the same plane. So they're not going in random directions, they're all going pretty much in the same plane, because all the planets were formed at the same time in a disk that was spinning around, and that disk is where the planets were, so they're all going in the same plane spinning around the sun. When we get to other objects like the TNOs, which are ones like Pluto and Charon, its moon, and there's many other ones out there, there's several hundred of them, they're all going in random directions, so they were formed completely differently. All right, and we'll get to that when we talk about that later in the semester. Now when we talk about the solar system, remember this is nothing to do with reality, meaning the scale of this is completely wrong. And we'll talk about that in a minute. But first I want to talk about how we measure distances. Now when we measure distances in astronomy, it's not convenient to use normal units, units like we use on Earth. If we just go from the Earth to the Sun, this can be written in many different ways. We can write this as 150 million kilometers, which is also equivalent to 93 million miles. But those are very big numbers, and those numbers have a lot, they don't have a lot of meaning, especially when you get out to here and you say, oh, Uranus is out here at over 1 billion miles away. Our brain can't conceptualize 1 billion miles. So it's easier for us to think of other ways to measure distances in the solar system. One of the easiest ways is to say, hey, let's use Earth as our reference point. Remember, the Earth doesn't go around in a perfect circle. So these are what we call the average distance. Sometimes we get closer, sometimes we get further from the sun as we orbit around it. But we're going to create a new unit. What we're going to call it is an astronomical unit. Astronomical unit. Which is the average distance from the sun to the Earth. And one astronomical unit is equal to 93 million miles or 150 million kilometers. So for dealing with solar system things, this is the easiest way to think of it. So we think of everything in terms of how far it is as compared to the Earth. For example, Mercury is at about 0.44 AUs, which means it's at 44% of the distance from the sun to the Earth. Venus is at about 0.7. So you get a rough idea how far they are as compared to how far the Earth is. Mars is 1.6. Jupiter is 5. Notice the distances here get much, much bigger. Saturn jumps all the way out to 10. And they continue to get bigger as you go. So when we talk about astronomy, we're going to talk about, we usually make this simpler and just call it an AU. An astronomical unit is just an AU. So we're going to say everything in terms of AUs. So when we talk about how far things are away, normally in the solar system we talk about AUs. But there are a couple other important things I want you to know. First of all, is I want you to know what the speed of light is. The speed of light is 300,000 kilometers per second. Not exactly, we round that up. It's actually 299,990.5. They have it calculated to so many digits. We know it precisely, as precise as instruments can make it nowadays. But the speed of light, why is that important to us? Well, you got to remember the speed of light is that almost everything we detect from here, we detect by the light coming to us. The only object we've actually brought things back from to Earth to analyze it is we have some material from the moon. Of course, the astronauts brought back a lot of lunar rocks. We also have a little bit of stuff from asteroids, where they sent a mission out, grabbed material, and brought it back to the Earth. But that's pretty much it. They're looking at doing a return mission from Mars, where they go to Mars and scoop up some of the rocks and soil, and then launch it back to Earth, but that has not been done yet. All the stuff we know about is by sending probes out there, they analyze it, and they send the information back to Earth. All right, but the speed of light, even though it's really fast, 300,000 kilometers per second is fast, meaning it can go around the Earth about 7 times in 1 second. How far, then, are we from the sun in terms of how long it takes light to get to us? Notice it goes 300,000 kilometers a second, but we're 150 million kilometers away. So if we do some very simple physics, remember distance is just equal to velocity times time. So if we want to know how long, we can just say, oh, time is just distance over velocity. But in our case, we know the distance. The distance is 150 million kilometers over the speed, which is 300,000 kilometers per second. Okay. Now, this is very simple. Look, we can do the magic zero crossing property. Actually, we're just dividing the top and bottom by 100,000, and we end up with 1,500 divided by 3. Well, that just equals 500 seconds. So light coming from the sun takes 500 seconds to get from the sun to us. Well, if we do that in minutes, you divide that by 60, you're going to get that 8.3 minutes. So when we look at the sun, we don't really see the sun the way it is now. We're seeing the sun the way it was 8.3 minutes ago. Now, it gets bigger when you go to further distances out here. These can be 30, 40, even hours later. When they sent the probes past Uranus and Neptune, and the one that went past Pluto, the New Horizons one just a few years ago, they had to send signals to it hours in advance to tell it, oh, your camera has to turn like this and shoot this picture. Well, you have to tell it way in advance because it takes hours for that signal to reach the spacecraft. And once it takes the pictures, it takes hours for them to come back again, too. So, we have another way to write our distance down here. We can also say we're 8.3